Could life itself have begun on Earth after arriving from the depths of space, frozen inside interstellar comets that still drift between the stars? For generations, we've wondered how life began, whether in the warmth of a shallow tide pool, the chemical crucible of a deep-sea vent, or perhaps in the icy heart of a comet. The notion that Earth was seeded from beyond is not new. It's been called the Panspermia hypothesis, the idea that life might travel between worlds, or even between stars. Indeed, it was one of the early favorites, but lost favor to more terrestrial origins, except for sci-fi circles. What once sounded like science fiction has gained new attention as we uncover organic molecules in interstellar dust, amino acids on meteorites, and comets rich in carbon chemistry, and now comets from far away. Each new discovery raised the possibility that our world may not have been the birthplace of life, but merely one of its many destinations, and that the process might still be happening, even now, with alien microbes drifting silently through the void aboard interstellar comets like Oumuamua and 3I Atlas. From ancient seeds to modern science, the story of Panspermia begins with a simple and important question: where did life truly begin? When early scientists like Nicholas Steno and later Charles Darwin began revealing Earth's deep history, it became clear that life must have emerged billions of years ago. But how it did so remained elusive. By the mid-19th century, experiments were already ruling out the idea of spontaneous generation, abiogenesis, that life could simply appear in rotting meat or stagnant water, even as the fossil record suggested that all living things shared common ancestors. That paradox led some thinkers to look beyond Earth itself for answers. In 1903, Svante Arrhenius proposed that microscopic spores might be pushed between worlds by the pressure of starlight, a concept known as radiopanspermia. Later, DNA pioneer Francis Crick and Leslie Ordrell took the idea even further, suggesting an ancient civilization might have deliberately seeded other worlds with microbes, what we call directed panspermia. But even without alien gardeners, the universe provides plenty of natural couriers: comets, asteroids, and planetary debris blasted into space by ancient impacts. Modern evidence makes this idea harder to dismiss. We have found organic compounds, from formaldehyde to complex hydrocarbons and even amino acids, in interstellar dust and cometary tails. Meteorites from Mars show that rocks can travel between planets without being sterilized by radiation or heat. Our upcoming Mars sample return missions could also provide clues. If Martian microbes share our biochemistry, that might be the first direct evidence that life travels easily between worlds. Many microorganisms on Earth can survive extreme cold, vacuum, and high radiation doses, lying dormant for millennia, and the icy comets and asteroids that once bombarded the young Earth were rich in both water and organic chemistry, precisely the ingredients needed to jumpstart biology. It is entirely possible that life emerged more than once, through several competing processes. The classic tidal pool and thermal vent theories remain very strong contenders, but panspermia adds a new dimension, that life might have originated elsewhere and found its first stable foothold here. Some versions of this hypothesis are almost certainly true in a limited sense, what we now call soft panspermia, since the heavy elements and organic compounds essential to life were forged in the hearts of ancient stars and spread through space by supernovae and cosmic dust. We are star stuff, and moreover, current theories are that our oceans arrived by cometary bombardment some millions of years after the collision that formed our moon. Life might have arrived then, or the chemicals needed for it, and if not on Earth, it might be how other worlds gained their start. One interesting aspect is that if that is true, it would mean such materials fell down on Mars and Venus and other planets too, and thus might have shared a source of life if they ever had it. More speculative forms, like lithopanspermia, imagine entire microbes surviving inside ejected planetary rocks. Radiopanspermia again considers interstellar travel on microscopic grains, and directed panspermia raises the possibility of deliberate seeding. Whether natural or intentional, the unifying idea is that life is not a local accident, it's a cosmic phenomenon. If even one of these mechanisms works, then the same spark that kindled life here may have flickered countless times across the galaxy, perhaps even continuing today aboard the silent, frozen emissaries we call comets. Comets as cosmic cradles. When we imagine the birthplace of life, we usually think of oceans or volcanoes, but in truth, comets may be the most fertile laboratories in the cosmos. Small, cold, and ancient, they are relics of the early solar system, filled with the same ingredients that built our world: water, carbon, nitrogen, a host of organic molecules. Far from being inert chunks of ice, comets are chemical engines, their surfaces sculpted by sunlight, their interiors worn by trace amounts of radioactive decay, and their thin layers of gas and dust exposed to ultraviolet radiation that can drive complex reactions. We have now seen this firsthand. Missions like Stardust and Rosetta have found amino acids, sugars, and organic compounds coating cometary dust grains. Many of these molecules are identical to those found in living organisms, or can serve as their precursors. In the near vacuum of space, these substances can remain stable for millions of years, protected by layers of ice and rock. As a comet approaches a star, sublimation and outgassing churn this chemistry into motion, a process that in its own slow way mimics the dynamic environments thought to have nurtured life on early Earth. Comets also solve another problem: volume and surface area. The number of comets and icy bodies in the solar system far exceeds that of planets, and each provides a unique microenvironment where chemistry can unfold. The Kuiper Belt and Oort cloud alone contain trillions of such worlds, likely even more in the past, and the galaxy may contain quadrillions more. On these tiny frozen spheres, with surface reactions powered by sunlight and internal warmth from radioactive isotopes, liquid films could form just long enough for complex chemistry and perhaps primitive life to emerge. A key point too is that smaller bodies have far more surface area per unit of mass than a planet does. It would take roughly 2 million Halley's comets to match Earth's surface area, but about 30 billion to equal its mass. That means an equal mass of comets of this size would offer around 15,000 times more surface area for chemistry to occur, and Halley's is a large comet. Smaller ones would have an even greater ratio. And even if that spark never ignited, these worlds could still be great carriers of potential, delivering water and prebiotic material to young planets. As I said, Earth itself may owe its oceans, and perhaps its earliest biochemistry, to the comets that bombarded it during the late heavy bombardment. In that sense, comets were both the architects and midwives of life, and they played that role here. They likely have done so elsewhere too. Alien visitors, Oumuamua and 3I Atlas. For most of history, we assumed comets were local, born and bound within our solar system. We did assume you occasionally had interstellar ejections and travelers, but not many, and we had none documented. But that changed in 2017, when a strange object came streaking through the inner system at hyperbolic speed. It wasn't following any familiar orbit. It came from the stars and was leaving for them again. We named it Oumuamua, a messenger from afar arriving first. Unlike any comet or asteroid we'd ever seen, Oumuamua tumbled erratically, showed no visible tail, and seemed to accelerate slightly as it left the sun's gravity, perhaps from outgassing or some other unknown force. Its shape and behavior sparked fierce debate. Was it an icy shard stripped of volatiles, a fragment of an alien planet, or even a probe, long dormant, now passing through unnoticed? Then came 2I Borisov, the first confirmed interstellar comet, in 2019, followed recently by 3I Atlas, another icy traveler thought to share a similar origin. These discoveries shattered any illusion that interstellar visitors were rare. If 2 or 3 could wander through our tiny observational window in just a few years and get noticed, there must be billions moving quietly through the galaxy at any given time. Each one is a potential seed ship of nature's own making, carrying ices, organics, and perhaps microscopic hitchhikers from distant suns. In a galaxy of 400 billion stars, even if only a fraction of those systems eject a few comets each century, the interstellar medium would soon be filled with a diffuse migration of life-bearing debris. Over millions of years, these wanderers could cross the gulfs between stars, occasionally falling into young planetary systems and delivering their frozen cargo. Collisions and fragmentations could spread the sea between such bodies too. If interstellar panspermia occurs at all, this would be one of its main highways, a slow, steady diffusion of life through the stars, one comet at a time. The odds of any single object bringing life to a planet might be infinitesimal, but given enough time and enough comets, the improbable becomes inevitable. It is an elegant thought that somewhere in the distant past, One such traveler may have brushed the newborn Earth, melted in our skies, and left behind a handful of living molecules that grew into everything we know. And it's even more humbling to consider that as you watch this, others may be on their way, alien comets still carrying the seeds of life, adrift among the stars. As a caveat, you must be wondering how life mostly bound to the surface of a comet could survive atmospheric entry, and that is problematic but doable. However, keep in mind that while it may have taken millions of comets to fill our oceans, the first fraction of those did not have a thick atmosphere to go through. There's probably a period where the ocean is thick enough to break such a drop. The comet probably fragmenting on impact where some bits would land and float, and when the atmosphere was thick enough to act as a strong limiting factor. You'd also expect a lot of pockets and craters that would experience less of the entry forces. We are talking about many millions, if not billions, of such bodies hitting our world. Only one had to survive, with a single surviving protocell. Now, I tend to favor other, better-known origins of life theories that have better cases, particularly in how the conditions would permit that first protocell, as opposed to comets acting as cold distributors of material, but panspermia remains a decent and scientifically plausible option, at least most forms of it. Some are a bit out there. Comet distribution networks. If comets are the couriers of life within a solar system, then the galaxy itself may be their highway. The smallest fragments of dust and ice, sometimes no bigger than a bacterium, are constantly being lifted from comets, asteroids, and planetary atmospheres by stellar winds and radiation pressure. These microscopic travelers drift outward into interstellar space, where they may ride on streams of galactic dust or be swept up into expanding shells of ancient supernovae. This concept, known as radiopanspermia, once seemed fanciful, but modern astronomy has found that interstellar grains can indeed survive for millions of years, and some are even coated with organic material. The same processes that scatter the ashes of stars could also scatter the precursors of life. A single dying sun might send trillions of such particles across light years, each one carrying traces of chemistry that once thrived in its system. Larger carriers may also play a role. Rogue planets, worlds flung from their birth systems, could drift between the stars for eons, retaining thick atmospheres or subsurface oceans worn by radioactive decay. Such planets might serve as slow but steady arcs of biology, preserving life in darkness until captured by a new star. And after all, our current primary theory for the origin of life does hold that things began in darkness deep under the sea. Likewise, interstellar comets, asteroids, and even debris from collisions between such bodies can continually exchange material, forming a vast slow-motion circulation of matter through the Milky Way. In that light, our galaxy begins to look less like a collection of isolated islands and more like a galactic biosphere, a web of worlds sharing that same cosmic gene pool. Life, in this view, is not confined to any one cradle, but constantly mixed and reseeded, a process so gradual that it takes billions of years, yet so pervasive that nearly every world receives its share of the dust. If nature can scatter life through the stars by accident, it's only a matter of time before intelligence learns to do so on purpose. Directed panspermia and artificial seeding. Of course, not every seed must be scattered by accident. As I said earlier, Francis Crick and Leslie Oldrill in the 70s proposed the idea of directed panspermia, that life on Earth might have been planted intentionally by an earlier civilization. While that notion remains speculative, it raises an uncomfortable symmetry. If it could be done to us, we might one day do the same. Humanity has already considered this. Concepts like the Genesis Project or World Seed Ships imagine sending automated probes to barren exoplanets, carrying microbial cultures or digital DNA libraries to spark ecosystems long after our passing. Tiny self-replicating machines, von Neumann probes, could spread these seeds far more efficiently than natural comets ever could. In a sense, this would be turning panspermia from a passive cosmic process into an act of deliberate creation. For my part, it's not that I doubt this could be done, I just tend to think we have far superior options to get done faster and better, and so I assume aliens would too, but time will tell. As of now, we have very little evidence that life is spread anywhere by natural or intentional means. There are, of course, ethical questions. Should we sow life on other worlds before we know whether they are truly lifeless? Would we be giving rise to alien biospheres, or erasing the chance to study ones that nature already built? We tend to assume planets with existing life would be robust against invasive species coming in from space, but what happens if one lands on a planet that already has fragile life and they have to get in a cage match? And if we discover that Earth itself was seeded in this way, would that make us artificial, or merely the next link in a chain stretching across cosmic time? It's even been suggested that some alien comets could be examples of this very practice, engineered seed ships disguised as natural ice balls, meant to blend invisibly into the background of interstellar debris. To us, they would look no different from Oumuamua or 3i Atlas, but inside they might carry life by design rather than by accident. A big quasi-comet like 3i Atlas might make a nice curio ship for fire out smaller ice balls and pods as one passes through a star system. Whether natural or intentional, both routes serve the same grand outcome, the universe ensuring that life does not remain confined to a single world.
Panspermia is about life traveling between worlds, but sometimes you can discover whole new worlds just traveling across this one. Back when I was stationed in Germany, one of my favorite hobbies was jumping on a train or a bus and just seeing where it led. If you love experiencing a city the way it's meant to be experienced, check out Day Pass, a Nebula original from Jason Slaughter, creator of Not Just Bikes. In each episode, Jason drops into a new city with one goal: buy a transit day pass and ride everything. Trains, trams, buses, boats, even funiculars. Try to see as much as possible before sunset. It's part travel challenge, part transit deep dive, and part how did I end up lost in a castle. It's thoughtful, funny, and a great reminder that public transit isn't just infrastructure, it's adventure. And while you're there, my Nebula exclusive this month is Lazarus Protocols, exploring how civilizations might freeze, preserve, or resurrect themselves after a catastrophe. Every episode of SFA premieres on Nebula early and ad-free. Use my link or QR code for 50% off an annual plan, just $30 for the whole year, and start watching today.
Panspermia and the Fermi Paradox Revisited. If panspermia works so well, it deepens one of the greatest mysteries in science, the Fermi Paradox. If life spreads easily through space, why don't we see it everywhere? Why, in a galaxy that may have been fertile for 10 billion years, do we find no obvious signs of intelligence? One answer is that life may indeed be common, but intelligence rare. Microbial ecosystems could thrive across countless worlds, quietly evolving but seldom reaching complexity or consciousness. Another possibility is that life frequently arises only to be erased by sterilization events, gamma-ray bursts, supernovae, or rogue impacts that reset entire regions of the galaxy. It may also be that panspermia tends to seed only simple forms. The journey between stars is harsh, and hardy microbes or spores are far more likely to survive than multicellular creatures. Evolution beyond that stage may depend on highly specific planetary conditions, making complex life a rare blossom in a vast microbial garden. And there is always the humbling possibility that we are the proof that Earth itself is one of those seeded worlds, the product of some ancient exchange of life between systems. If so, then every cell on this planet carries within it the legacy of an older cosmos, a story written not in myths but in molecules. So rather than solving the Fermi Paradox, panspermia reframes it. Perhaps the galaxy is already full of life, just not the kind that builds radios or rockets. We may be surrounded by our kin, descendants of the same primordial chemistry, whispering across the stars not in signals, but in shared code of DNA. Testing the hypothesis and speculative extensions. If the panspermia hypothesis is true, we should be able to find traces of it, but proving that life has traveled between the stars is one of the hardest experiments imaginable. The evidence would have to bridge both chemistry and history, showing that two biospheres share a common ancestry older than the planet. The search is underway. NASA's OSIRIS-REx has already returned samples from asteroid Bennu, rich in organics that predate Earth itself. JAXA's Hayabusa 2 brought back grains from Ryugu, confirming that complex carbon compounds form naturally in space. The upcoming Comet Interceptor mission aims to study a pristine comet, possibly even an interstellar one, before it ever approaches the Sun, giving us our first look at materials that may never have been part of our solar system. Meanwhile, Dragonfly, the nuclear-powered rotocraft designed for Titan, will examine a world where organic chemistry may already be taking its first biological steps. Each of these missions inches us closer to testing panspermia in practice rather than in theory. There are also subtler tests. Life on Earth uses left-handed amino acids and right-handed sugars, a chemical asymmetry known as chirality. If we ever find elsewhere with the same bias, that could suggest a shared origin. If its chemistries were mirrored, it might mean a separate genesis. Similarly, isotopic ratios of the discovery of identical DNA bases on multiple worlds would be strong hints that life, or at least its toolkit, migrates through space. Even microbes in our own upper atmosphere or on the moon's surface might bear witness to how easily biology can hitch a ride beyond Earth. Future experiments may go further. Artificial comet laboratories in orbit could mix organic compounds under cosmic radiation to see whether self-replicating chemistry emerges. Sample return missions to the moons of Europa and Enceladus might reveal whether life beneath their icy shells shares our genetic alphabet, should it exist at all, of course. And eventually, as our interstellar probes leave the heliosphere, we could directly sample the dust between the stars to look for frozen cells or complex organics adrift in the void. All this brings us to more speculative frontiers. If life is already being spread naturally, how far could that process reach? Intelligent species on spaceships are presumably orders of magnitude faster and better, but in the absence of that, it should be viable. Over billions of years, the steady diffusion of spores, dust, and frozen organics could form what might be called galactic mycelium, a network of life's chemistry stretching across light years, linking world to world like filaments of cosmic fungus. Each planetary biosphere would be one fruiting body in a far larger organism, exchanging genetic information through impacts, stellar winds, and comets. From that perspective, evolution itself becomes a cooperative galaxy-wide enterprise, a slow distribution across time and distance. It's an image that comes naturally to mind, just as fungal networks span continents, and we imagine alien fungal networks on a planet forming a giant mushroom mind. We could have some interstellar life form, or brain spanning whole star clusters, or even the whole galaxy. Even more exotic possibilities remain open. Some researchers speculate that alien life might not rely on carbon and water at all, but on silicon, ammonia, or even magnetic or quantum structures that store and replicate information in unfamiliar ways. We have episodes discussing many of these options, and they make good cases. If such entities exist, they could survive where nothing biological could, perhaps inhabiting magnetic fields of stars or cold voids between galaxies. Life, in that sense, could be not just widespread, but fundamentally unrecognizable. And then there is time itself. Could frozen spores persist for eons, waiting out the death of stars? Could information encoded in durable minerals or self-repairing nanostructures survive from one galactic epoch to the next? If so, then panspermia is not only a story of space, but of endurance, life refusing to let the clock run out. Yet even without such speculations, the philosophical weight of panspermia is profound. It blurs the lines between the local and the cosmic, between the living and the lifeless. It suggests the universe is not a sterile backdrop where life arose once by chance, but a vast and ancient ecosystem where biology is as natural as starlight. If comets are the messengers of that continuity, then every falling star we see is more than debris. It is a reminder that we, too, may be the children of a wandering seed. So perhaps the question is not whether life began on Earth or among the stars, but whether there is truly a difference. If the same chemistry courses through every world, then all living things share one ancestry, written in dust and ice. The atoms that make us once drifted through space, before coalescing into oceans and cells, and long after we are gone, they will scatter again, carrying traces of us to new horizons. If that is the nature of life, to spread, adapt, and endure, then panspermia is not a theory but an inevitability. The universe itself is a gardener, every comet is its hand at work. Perhaps the next Oumuamua we spot will not just be rock and ice, but a true messenger, carrying the echo of a shared origin among the stars. And if we are the children of alien comets, then perhaps we were never alone at all, merely waiting, through the long silence of the stars, for the rest of creation to awaken.